Today's video is on binding energy and nuclear stability. Yeah.
So today we'll talk about binding energy and nuclear stability. We started with nucleus and particles. From there we looked at isotopes, stable and unstable nuclei. We looked at radioactive decay and some of the radioactive decay reactions. We looked at decay curves and half-life. And this brings us inevitably to nuclear stability, which is where we find ourselves now. I guess the question is, which nuclei do which decay reactions, and why? Let's consider a nucleus of beryllium-9. I've chosen beryllium-9 just because it's easy to draw. So let's see what beryllium-9 really means. Well, it's 9 over 4 beryllium, which means we have 4 protons and 9 as 4, 5 neutrons. So total mass of 9, atomic number of 4 protons, total mass of 9, 5 neutrons. Here are the protons drawn in red and the neutrons shown schematically in green. Remember the Coulomb's law of electrostatic attraction, K, Q1, Q2 over R squared, and certainly give us all the electrostatic forces. This tells us that these positively charged protons should repel one another. You can see these orange repulsive forces felt back and forth between all of the protons. And these forces are very powerful because the charges are large and the distances are small. So here's these repulsive forces inside the nucleus. Of course, this picture is in 2D, the real one's in 3D. This picture is still, the real one is vibrating. This picture is obviously too large, nuclei are much smaller. And also in our diagram here, protons and neutrons look like solid spheres, but really they're not. Now, let's see what we mean by really they're not. We do need to justify the continued existence of the atomic nuclei against this tremendous electrostatic force that's driving them apart. Just think about it for a second. These very strong proton-to-proton repulsions are pushing the nucleus apart. Why does the nucleus stick together? In order to do that, let's look inside the neutrons and the protons. So if we look in there, you're going to see there must be some kind of stronger still force inside the nucleus holding it together. And our question for today has to be, what is the force and where does it come from? I'm going to suggest we look inside the neutrons and protons and try and discover the origin of this powerful force inside there. So here we are, let's look inside the neutrons and the protons. First of all, the first thing we notice if we actually look at a proton or a neutron, if we manage to get up close, that they don't have solid outside boundaries. They are not solid little spheres the way we might imagine. They seem to be made up of various particles going around inside, and the particles going around inside protons and nuclei, or protons and neutrons, we call quarks. So the proton has 2 up quarks and a down quark with positive 2/3 charges each and negative 1/3 charge in a down quark. Neutrons made of 2 down quarks and an up quark, negative 1/3, negative 1/3, and plus 2/3. So you'll see that the total sum of charge in a proton is +1, and the sum of the internal charges is 0 on the neutron. This is a strong, balanced, mutually attractive force that holds the quarks inside the neutron together. And this attraction of the quarks inside the neutron we consider to be the basis for nuclear stability. It's so strong that it is felt by nearby particles, such as other neutrons and protons, and that very strong force, if you want, leaking out of the neutron between its mutually attractive internal constituents, we call the strong nuclear force. And this is the force that's strong enough to overcome the mutual proton-to-proton repulsions inside of a nucleus. You might say neutrons act as a glue for nuclei. So here's that diagram, or another one very similar, and you can see that the neutrons are having these attractive forces to the neighboring particles. They're red, that's a strong nuclear force, and then the black electrostatic repulsions are shown here pushing the nuclei apart. So if you have the neutrons there, they can help to glue the nucleus together. And the binding energy is greater than the electrostatic repulsion, so the nucleus stays connected. What combinations of protons and neutrons make up stable nuclei? Well, here are some configurations of stable nuclei, and you'll notice that as we have increasing number of protons, we need increasing neutrons. It turns out no number of protons above 84 protons will be stable. If you have more protons than this, you have to decay, lose protons and gain neutrons. If you have too many neutrons, you have to lose neutrons and gain protons. And if you simply are above 84 protons, you have to decay down to less than that. So in this top quadrant, we see beta decay. So here we have calcium 100 decaying down to, away from calcium 100 down to scandium, I think that is 100. And you see the calcium, yes, scandium. You see the calcium losing a neutron, gaining a proton, and going down to scandium, and eventually reaching that stable zone. Down in the lower, the green quadrant, we have positron decay, and that's what happens when something like this 115, TB115 here, decays with a positron, making GD115 or gadolinium 115. So these reactions look like losing a proton and gaining a neutron. If you are outside the zone of stability, like astatine 184 here, then you have to lose alpha particles, protons and neutrons going down here until you get into the blue zone and then start positron decay or electron capture. All of this then just justifies why some particles are stable, that is why some nuclei can stay together, why others cannot, they have either too many or too few neutrons, and why different unstable nuclei do different reactions along their journey. Why does a nucleus that has too many neutrons do one thing as one that has too many protons do another? They have to get towards this stable zone, and of course there's different types of reactions to do it. Thanks everyone, and see you soon. Don't forget, have a look at our next 2 videos and stay tuned to our next lesson 31, Electrons and Wave Behavior. Electrons and wave behavior.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!